of differential calculus. Folks, you got to be with me here. So, so what we're going to do is we're going to learn a different type of form to represent a derivative, and then from that we're going to kind of use it to apply or use some applications in some, I think, an interesting way, and this is going to lead into the robot project. And then after that, we're going to get into antiderivatives, so integral calculus. All right. So there's a lot of interesting stuff coming, and it's all going to be related to this concept. So this is the bridge. Now it does rely on you having a strong grasp of differentiation. All right. So taking derivatives. So if you think about what we've been doing throughout the entire course, I mean, aside from limits, which is really just there to help us learn what a derivative was, the course so far, and we're more than halfway through, has all been about understanding a derivative and how to find a derivative, right? So there's a reason for that, because antiderivatives are a whole lot easier if you know derivatives, right? So if I were to say the derivative of sine is, you would follow that with cosine, right? So if I tell you an antiderivative is going backwards, if I were to say what's the antiderivative of cosine, you would say sine, right? Without even a moment's hesitation, because you know the derivative of sine is cosine, so going the other way is not going to be challenging because you have instant recall on sine to cosine, tangent to secant squared, right? Natural log to 1 over x, right? So when you see it in its derivative form, going the other way is not going to be a challenge, right? But what's going to happen is there's going to be some expressions that are in disguise, right? So you'll have to manipulate it algebraically or using some knowledge of pre-calc to get it into a form that is convenient, right? So imagine you have this really complicated trigonometric expression. You know, we don't even have to write down one. You just have this really complicated expression that if you apply some identities and clean it up, it eventually simplifies down to secant squared. Then you would say, okay, well, the antiderivative of secant squared is tangent. That's my answer, right? But you have to do all the steps to get it into the form of secant squared before you make that realization, right? This is the building blocks of that. But it does start with the concept of taking a derivative. And one of the weird things that you're going to find as we move forward, when we take antiderivatives, part of the process in many techniques for finding an antiderivative is actually finding the derivative. So we're going to be using a derivative to find an antiderivative. It's a weird thing to think about. But for now, we're just working on notation. So y equals x to the fifth plus 37x, I'm going to say dy dx is equal to 5x to the fourth plus 37. All right, that's nothing new. All right, what this is known as a differential equation. All right, a differential equation. Now, that should be fine because it's an equation. Differentiation is another way of saying derivative. So put those two ideas together, it kind of makes sense. What we're going to do now, though, is we're going to multiply both sides by the dx. All right, so algebraically, we're just going to multiply both sides by dx. So I'm going to get dy is equal to 5x to the fourth plus 37, that whole thing multiplied by dx. This is known as the differential form. All right. So you look at this and you say, wait, okay, this isn't complicated at all because all I have to do is take a derivative and move the dx to the other side. That's wonderful. The applications of this are pronounced. There's a lot going on here. Because if we really think about what each of these things reference, there really is a lot going on here. So this is a small change in y. All right. This would be some small change in x. right? Actually, an infinitesimal change in y and x. Instantaneous even, but it's kind of hard to think about something being instantaneous and also having a change. It's kind of weird, but that's where the tangent line concept comes into play. All right, that inner function, that's the derivative function. But what we're really dealing with is the idea. Let me denote that as, I'll just call it f prime. This serves as a product. Okay? So really what that's boiling down to, I'll just do it on the sideboard because you don't really need the diagram. It's just more for like hand waving. But let's say you have some kind of function, arbitrary function, that we're calling the derivative function f prime. Okay? That's what this 5x to the fourth plus 37 would represent. All right? This function, every distance from the x-axis to a point, vertical distance to a point on that line, would be a measure of f prime. All right? What I'm saying here is that I'm multiplying that by some teensy tiny horizontal change. Right? So if I create some teensy tiny horizontal change, I create a rectangle. All right, so that's a dx. What I would get by multiplying these two things, this inner space, f prime times dx, would be the area that's bounded within that rectangle. So I'll just say the area of the rectangle. All right, so moving forward, what we're going to be able to do using a concept called integration is we're going to be able to take all of the little areas that exist with these characteristics from the beginning of an interval to the end of an interval, every one of those little areas, and compile them all together. And what that'll end up giving us would be the area under a curve. All right? So what that in turn gives us is a way to come up with areas and then, by extension, volumes related to, I'll just call them funky figures, funky geometric figures, right? So you're not just limited to cylinders, spheres, and things like that. You could find areas and volumes related to anything, right? All with calculus. And some of the activities that we do moving forward are going to relate to that, right? So, but as far as these problems are concerned, I'll do number 3. What are we really doing? dy dx secant squared times 2x times the derivative of your inner function of 2, and then swing the dx over. So dy is equal to, I'll call it 2 secant squared 2x dx. All right? That's all I'm really looking for is the differential form. But again, knowing what each thing represents tells us more of the story.
So, like, what does a differential form actually mean? Is that like an area equation and you just plug in points?
Well, it's an area equation, but you plug in, you can plug in particular x values, and if you know the dx and the dy, you can do that. But what we're going to do is we're going to introduce another concept called integration that's going to allow us to do it algebraically. So, and the calculator has some nice shortcuts to that also. So, but that's really the subject of the next unit. This is kind of like a teaser. It's a teaser trailer. And I'll put stars on 2 and 4 so you can try those on your own if you want. I'll leave it up to you because what we're going to do with this is really more important than just actually carrying out the process. So there's a lot of notation here, and for some reason it's cut off on my page. But I've been having this problem recently. It does that, but then when I scroll back, it's fine. I don't know. It's like a buffering issue.
That's really weird.
Yeah, I did that in stats. I don't know why. I think it's just a connectivity issue. Oh, we'll see. Because this automatically gets backed up in real time, so it just might be that. So anyway, this is a really, it's a busy diagram. It's a very, very busy diagram. I'll explain it to you, but I don't know that making use of this diagram is going to be the best way to go. This is the classic textbook definition. If you can interpret all the notation and everything, it makes perfect sense. Like the math teachers. But like for a person learning it for the first time, it's like, yeah, what are those rectangles all about? Yeah, those are just bracketing off spaces and stuff like that. So what I'll do again is just kind of go off on the side, draw a quick diagram for you, and give you a true sense of what it's talking about. It's actually a very easy concept, but again, it's kind of weird. So we have this idea, the delta f. Delta f represents a change in a function, right? So that's what I'm going to do. I'm going to draw an arbitrary function. Right? Same arbitrary function as always, which means they're not arbitrary. All delta f is telling us to do is find 2 points on the curve, all right, 2 points that are separated by space. Now, if I connect them with a straight line segment, what would that line segment be called? 2 points separated? Not a tangent. The thing that came before that. Secant. All right. So a secant has a slope that's defined by the change in y and the change in x. All right, but the triangle change, right? The capital delta. All right. F and y are the same conceptually as long as it's a function, so I can call this delta f. All right. So what I can get is if I have some change in x corresponding to that change in y, I have a way of predicting these values. So basically what this is saying is if I have a value that starts at, we'll call this a. If I have a plus delta x, so that would get me to this location, I'm going to have some corresponding change in my function value. All right. So you'd have necessarily an f of a plus delta x. So the beginnings of the difference quotient. All right. So it's really along the same lines as if you had a, that would correspond to f of a. All right. There's nothing different there. All right. It's just at a particular point. So that's secant. Okay, that's going way back to like October. Now, what I'm saying here is if you introduce a tangent line, I guess we'll do it in green. Depending on where you introduce that tangent line, it itself is going to have a slope. And that slope is defined based off of the derivative, all right, which we say is dy dx. All right. Now, this is the part that's strange, and that's why this diagram is such a disaster. But it's a beautiful disaster because it gets the job done. It has all the relevant information. It's just, boom, here's all the information all in one shot. What you have to do is kind of imagine that there's a little microscopic region of this line that we're really zooming in on. All right, so that's what I'll do. I'll really zoom in on. I put the green out. All right. So that line has a slope, and that slope is defined by the same characteristics as any slope would be. All right. Except it's on such an infinitesimal level that I wouldn't say it's delta y over delta x. I would say it's dy over dx. All right. So basically what this is saying is that we could do the same stuff with the tangent line that we could do for a secant line. If I wanted to estimate the change in a function, I can do it with the tangent line. The problem is, it's not always going to be a good estimator. Right? So if I look at, for example, trying to estimate some small change away from A here, the tangent line would be a good estimate because the tangent line happens to go through A. But if I wanted to estimate a change, let's say, over here, starting at this point, well, the slope at this location is vastly different than the slope of my tangent line. So the estimator from the tangent line slope it's not going to be anywhere near as good as it would be for, a tangent line that would be in this neighborhood, right? So part of our challenge when we were doing linearization, Newton's method, and all that was coming up with an A value that was convenient but also close to a point of tangency or vice versa. Right? So you have a point that you're looking for, you want to have a point of tangency that's close to that so that you could expect a reasonable approximation. Right? Was that Curry Honda a week ago, picking up my car because of a transmission issue, and I noticed a picture on the wall. And I've seen this picture before, but it was pretty spot on. Let me just pull it up real quick. It talked about braking distances and also tire tread. And I thought to myself, I'm like, this is probably not the best thing to admit, but this is what I think about in my own life. I was like, this is a great application of differentials. And then I start thinking about stuff like, like when you talk about cars, if you've ever heard the term like limited slip differential, positive traction and stuff like that, or quasi traction, if you ever saw that. I wonder if that's the same thing. I didn't even really look into it, but you have tread depth, and then you have the stopping distance. And you can see that it's a very minuscule change in tread depth. Now, the minimum legal limit is somewhere in this neighborhood. All right, for New York, it's a little bit longer than some other states. Like basically the northeastern regions and the northern regions, they allow or they don't allow under a certain amount of tread because of icy conditions. But if you're in like South Carolina, you can get away with a little bit more, right? But that's also why when they had, I think it was like 5 years ago, they had like the teensiest, tiniest little ice storm outside of Atlanta, and the whole state shut down because nobody could drive because everybody had fall tires, So, but this is showing us the stopping distance in car lengths. All right, so if you only have 1 30-second of tread on your tire, so like a little smidge of tread, so practically bald, it's going to take you 18 car lengths to stop from, it's usually 60 miles an hour or whatever it is, like 30 miles an hour or whatever the speed limit is, all right? But then you can see it's half that distance if you have 11 30 seconds, all right? Now, car length, what are we talking about, 10 feet-ish for an average size car? Yeah, for like a small to mid-sized car, yeah, in length. So we're talking about a difference of 90 feet. Like, I mean, that's a pile up on the highway. Like, that's a lot of dead people, all right? So it gives you a sense, but this is the concept of a differential. Just a teensy tiny change in your tread depth leads to a consequence in terms of stopping distance, all right? So then you say, okay, well, what about going from, the full tread to, okay, now we're getting into like minimum safety, like 5 30 seconds, 4 30 seconds, that region there. You're talking about roughly a difference of 2 car lengths, that's 20 feet. So now like you're on a back road, one of the legendary back roads in this area, and it's a little slippery out, and you're following too close. Person in front of you slams on the brakes for whatever reason, maybe they want to. Here, you're probably not going to rear end them. Here, you're probably going to rear end them. Right? So these are some things to consider, and these are also some things that we're going to look at in terms of the calculus of it to see where these values came from. So very, very powerful concept, I think, and so worth spending some time looking at. Yeah. So I'll just do one example for you just to kind of get the idea across. It's all calculation heavy. Function f changes when x changes from a to a plus dx. Find the absolute change, estimated change, and approximation error for each. All right, the idea here is that we wanted to develop an understanding of the most important one, which is the estimated change. Why do we think that's the case? Why is that one the most important one? Involves a derivative, sure.
Like a starting point.
Yeah, I mean, you can think of it that way. I mean, let's just put it this way. If I'm at the supermarket and I'm trying to determine whether I have enough money to purchase whatever I'm trying to purchase, I could break out the calculator, add up all the items, factor in sales tax, and then, I don't know, maybe start counting discounts for based off coupons. And then subtract. Okay, I'll be there for like half an hour extra. Or I can say, well, okay, this box of cereal is about $5. And it was really $4.50, but with tax, let's just say $5. This candy bar is $1.50, let's say $2. You know, and you do some overestimating so that you know you definitely have enough money. Right? So it gives us a quick and easy way of getting a sense of the value without having to get bogged down in the calculation. Also, I mean, the derivative part, we can't get lost in that. This is all pre-calc. Actually, I would even say this is algebra 1. The notation makes it look a lot more complicated, but this is just finding the difference between two y values given x values. You just put that in your calculator. Here's the calculus. Here's where we see if our estimate is a good one, right? So we take a derivative. So we have, and I recommend writing it as f prime. Two x plus 2. I like getting all the ingredients out of the way first. Okay, so one of the things I need to do is find a derivative. I know that. They told me the a, they told me the dx. I need an a plus dx, so I'll just kind of chuck this over here. A plus dx is equal to 0 plus 0.1, which is going to be 0.1. Right? And then I need f of that. But I also need the derivative at that a value, and as well as the original function at that a value. So a lot of calculations, just bang that out real quick. So I'm going to do f of a plus dx, which is the same as f of 0.1. Then I'm going to do f of a, we'll call it f. F of 0. Then I'm going to do my f prime of a, which is f prime of 0. Now, the most complicated calculation is this one. If you're going to have to use a calculator, it's probably going to be for this one. Everything else is easy. All right, f of a, I'm plugging in 0 for a, so 0. All right, same thing with the prime, just plugging in a 0 for a in turn for x, so that's going to give me a 2. This one I just got to chuck in the calculator, 0.1 squared plus 2.1. Well, actually it's 1.21 plus 0.1.41. I'll just double check that. Oh, 0.21. All right, so we just got to crunch it out. Delta F. The difference between these two values is 0.21. df would be the product of these two values, which is a 0.2. And then the difference, so the error. The absolute difference between the two. So subtract them and drop any negatives, 0.01. All right, so it's not far off at all. It's pretty spot on. I mean, it depends on how accurate you want to be, but it's right there. So when you're thinking about making an approximation, I would want to go with the estimated change.
Wait, where did the two come from?
This bad boy?
Yeah.
That goes from plugging the 0 into this derivative function. Right. Okay, so between today and tomorrow, you have time. You know how it is. So you just want to work through finishing the packet. All right. So you know what I mean. Not tomorrow.
Let's do Monday.
You'll have time in Monday, and Tuesday we'll start a GeoGebra activity just to kind of familiarize ourselves with that software, and then once we finish that, we'll start with the robots. So,
Is it Ollie again?
it will be Ollie again. It's going to be different
Different?
because we have more of the calculus twist to it.
Yeah.
It's going to be and I also made some adjustments based off of the feedback. One of it will be the differential component, like making a small change. So I figured, like, we have the straight track, but then the idea of like varying something. So maybe going up a ramp, so go up into the hallway.
Oh, that'd be cool.
Yeah, you know, so a little twist. So I think it'll still be interesting to you. Okay. Besides, get the robust. 0.21 comes from taking the value from you're gonna use A plus B. BF is